Hello everyone, welcome back to another video tutorial in integral calculus. But in this video, we will learn how to integrate functions using one of the important integration technique, that is trigonometric substitution. Okay, again, there are some of the functions that can't be integrated using the existing integration rule, such as the power rule, trigonometric integration, or trigonometric rule. Okay, so the first thing that we need to do if we encounter such function is to determine whether trigonometric substitution can be applied into that. Okay, so we need to apply trigonometric substitution, and the procedure for trigonometric substitution is just by changing the function of x into a trigonometric function. We convert an algebraic function into a trigonometric function. But before we proceed to the procedure for trigonometric substitution, it is very important that we first familiarize the trigonometric identity from or derived from the right triangle. Okay, so we have this right triangle, then Pythagorean theorem, that is, we have this hypotenuse, that is, this one is our hypotenuse, that is C. Again, the hypotenuse, that is the longest side in the right triangle, and we have A here, and B, that is the side of our right triangle. But if we have our angle here, theta, our A here represents the adjacent, or the adjacent of our angle theta, and B here, that is the opposite, or the opposite side of our theta. So if we determine the side of our C, then we apply Pythagorean theorem, that is C squared is equal to A squared plus B squared, or that is just C is equal to square root of A squared plus B squared. If you remember your trigonometry, if you want to determine A squared, the side or the length of our adjacent, that is just C squared, the hypotenuse squared, minus the opposite squared, or that could be A is equal to square root of C squared minus B squared. And now for B squared, the length of the opposite, that is just C squared minus A squared, or that is just B is equal to square root of C squared minus A squared. So these are from Pythagorean theorem, that is the length of the sides of our right triangle. Okay, so please review your trigonometry. Now let's how are we going to use this one to integrate functions? Okay, now take note, if we have function that involves square root of A squared minus U squared, okay, we have the square root of A squared plus U squared, or square root of U squared minus A squared, wherein our U here is any function of x, and our A here, that is constant. So if we have function that involves this type of function, then that would be our hint that we should apply trigonometric substitution. Okay, that's our clue that we need to apply trigosub in evaluating that integration. So how are we going to use this one? Now take note, if we have in the function, we have the square root of A squared minus U squared, then we set U in that case as A sine theta. Remember that one. Why is it U is equal to A sine theta? Now take note, if you have square root of A squared minus U squared, you are sure that our A here is the hypotenuse. Why? It's because if we have difference, or if we have minus sign in between two terms, that is from our Pythagorean theorem, that if we have minus sign in between, so that is our C there, that is our hypotenuse, diba, from our right triangle form. So therefore, if we try to draw the right triangle, this one is our A, and U here could be the opposite or the adjacent, because from this term it could be B squared or A squared, correct? It could be the opposite side or the adjacent side. Our U here could be the opposite side or the adjacent side in the right triangle. But if we have function of x, the best way here or is we set our u here as the opposite. Okay, we always put u as our opposite, though it can be assigned as the adjacent, but the most appropriate or the most easiest way is that we set u as the opposite. Okay, so if this is our theta. Now, if we create a trigonometric identity from this triangle, from our SOHCAHTOA, if you remember, that if we have sine theta, that is equal to opposite over the hypotenuse, correct? That is from So therefore, in this case, our sine theta is equal to, now look at this right triangle, sine theta is the opposite, is equal to opposite, that is u, correct, over the hypotenuse is a, this one. So therefore, we have a. So we can say that our u here is equal to a sine of theta. Again, our u is any function of x, and a is constant. So we have, if we have square root of a squared minus u squared, then we set that as our u is equal to a sine theta. So we set u as a sine theta, so we substitute it to our function. What if we have square root of a squared plus u squared? So we have square root of a squared plus u squared, and we set again u as any function of x, a is constant. So we know that these two, a and u, is either opposite or adjacent. Okay, since we have plus sign, going back to Pythagorean theorem, if we have positive sign in between, our a and our b here is either adjacent or the opposite. So therefore, if we try to plot that in our right triangle, we have u here, that is our opposite, always our function of x, the opposite side, and our a, that is the adjacent. Okay, so this is our theta. So the length of this side, that is the hypotenuse, is equal to Pythagorean theorem, that is u squared plus a squared. Okay, or a squared plus u squared. So therefore, we set, if we would like to get the trigonometric identity from this, we have tangent of theta is equal to opposite over adjacent from SOHCAHTOA, this one, that is we have tangent theta is equal to opposite over the adjacent, then we have opposite of theta is u, correct, and the adjacent of theta is a, so you have a. So therefore, we could say that our u here is equal to a tangent of theta. So what if we have square root of u squared minus a squared? Then if we plot that in our right triangle, we could say that our u here, from our Pythagorean theorem, if we have difference, the first number here, that is our hypotenuse. From Pythagorean theorem, c is the first number before the minus sign. So therefore, our u here is the hypotenuse. So this one is our u, correct? And a here, this one is the adjacent. So we have a here. It could be ang a na to, it could be adjacent or the opposite, since it could be b or the opposite or the adjacent. So if we place that at our adjacent sa tong angle theta, therefore the opposite here is equal to u squared minus a squared. Okay, so therefore we could have the cosine theta is equal to adjacent over the hypotenuse, correct, from ka. So therefore we have cosine of theta, that is the adjacent over the hypotenuse, that is u, correct, adjacent over the hypotenuse. So therefore we could say our u here is equal to a over cosine theta, and we know that 1 over cosine theta is equal to secant theta, correct? So therefore we could say that it is a, we have 1 over cosine theta, that is a secant of theta. So therefore our u is equal to a secant of theta. So in this case, all function of x should be substituted by trigonometric identity a sine theta, a tangent theta, or a secant theta, depending on the type of function that we have. Okay, and now we have integration rule here, a new integration rule, that is, if we have the integration of du over square root of a squared minus u squared, again our a here is constant, our u here is in a function of x, the result of this is equal to the arcsine of u over a plus c. Remember this one. Okay, so this is our rule number 1, that is the inverse trigonometric function. And then if we have this one, the integration of du over the u square root of u squared minus a squared, that is 1 over a arcsecant of u over a plus c. Okay, this is rule number 2, additional integration rule. And then lastly, we have the integration of du over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. So this is the third rule. And these are additional integration rule. Instead of memorizing this rule in integration, we can basically use trigonometric substitution. Okay, since these are derived using trigonometric substitution. Okay, let's try to prove this one. That is, if we have the integration of du over the square root of a squared minus u squared is equal to arcsine of u over a plus c. Let's try to prove. Now we know that if we have square root of a squared minus u squared, that is, if we try to plot that in our right triangle, a here, that is the hypotenuse, correct? And u there, that is the opposite. Since again, this resembles to the Pythagorean theorem, that is, if we have minus sign in between, the first term is the hypotenuse, correct? Going back to this rule, that is, if we have the first term, if we have difference, then our first term here, that is the hypotenuse from our right triangle. So we can label this longest side in our right triangle as a, that is the hypotenuse, and u here, that is the opposite. Always our function of x is the opposite side, and this one is what? Theta. And we know that the height or the length of this side from Pythagorean theorem, that is the hypotenuse squared minus the opposite squared, and that will give us square root of a squared minus u squared. So therefore we can create a trigonometric identity to this, that is secant, that is sine theta, that is the opposite over the hypotenuse, that is u over a. Okay, so therefore we can say that our u is equal to a sine of theta. So this function here must be changed using trigonometry. Okay, so we have to convert this function into a trigonometric function. Okay, now take note, since we have du here, so we need to derive this one so that we could have our du here, that is a cosine of theta d theta. Again, our a here, that is constant, so we just copy it. Then the derivative of sine theta is cosine theta d theta. So we can now use this one to sub in our integrand. So we have the integration of du over square root of a squared minus u squared. Then we have our du here, that is a cosine theta d theta, that is a cosine of theta d theta over, now we have square root of a squared minus u squared, correct? Now we know that from this, we could simply create another trigonometric identity involving adjacent. So what should be the trigonometric identity here that involves this side or this adjacent side here? We can use cosine, correct? Since if we have cosine of theta, we have adjacent. What is our adjacent? From cosine theta is equal to adjacent over the hypotenuse. So our adjacent here is square root of a squared minus u squared over the hypotenuse. From this case, the hypotenuse is a. So therefore, we have here the square root of a squared minus u squared is equal to a cosine of theta. So we have here the square root of a squared minus u squared, that is a cosine theta, this one. So we change this square root of a squared minus u squared as equal to a cosine theta. So we have here a cosine of theta, and then we have the integration. Now take note, we can cancel all this value here, correct? So the remaining would be the integration of d theta. Okay, that's in terms of theta. And we know that the integration of d theta is equal to, of course, theta plus c. Correct? So the same as the integration of dx is equal to x plus c. Now, take note, this should not be our answer. Since we have a variable theta, we substitute back our original function that is in terms of u. Now we know that from this equation, our theta here, that is equal to arcsine of u over a. Correct? That's the inverse function, or the inverse trigonometric function, in which our theta, that is the arcsine of u over a. So therefore, we substitute the value of theta here, that is arcsine u over a. So therefore, we have arcsine of u over a plus c. So therefore, this is the integration of du over square root of a squared minus u squared. Okay? So later, we will be solving problem that involves real numbers. So we have proven this rule here. Now we have second rule in inverse trigonometric function, that is the integration of du over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. Okay? So in this case, we will be trying to prove that this function is equal to this function. So we can use trigonometric substitution to this one. However, we need to plot first this a and u in our right triangle. We have, if this is our right triangle, we know that our a and u here is either in the opposite or the adjacent side of our angle theta, since none of this is hypotenuse. Again, since we have plus sign in between the two terms. We could only have hypotenuse if we have minus sign here, in which the first term is the hypotenuse. But in this case, we have positive sign in between. Then we have a here is the adjacent, and u here is the opposite. Okay? So therefore, this one here, the side, this hypotenuse here, that is a squared plus u squared. Okay, so again, if we have a squared plus u squared, we can use tangent here, that is tangent of theta is equal to u over a, correct? And then we have u is equal to a tangent of theta. Now, our goal here is to eliminate all the u function or u variable in our function. So, since we have derivative of u here, we need to get the derivative of u. That is, our derivative of u is equal to a secant squared theta d theta. This is from your differential calculus. So therefore, let's change du here as a secant squared theta d theta over, now how are we going to eliminate u? So we know that our u again is a tangent theta. Therefore, we could say that is a squared plus our u, that is a tangent theta, but it is squared. Take note, the squared sign, that is a tangent of theta squared. By further evaluating this function, that is, we have a secant of squared theta d theta over a squared plus a squared tangent squared theta. Now we can take out a squared outside of our function here. We have a secant squared theta d theta over, we can factor out a squared, that is we have a squared times 1 plus tangent squared theta. Now if you want to check your factor, you can multiply a squared times 1, that would give us a squared. If we multiply a squared times tangent squared theta, it will give you a squared tangent squared theta, correct? So therefore in this case we can say that it is a squared, don't forget the integral sign, theta d theta over, we have a squared. Now we know that 1 plus tangent squared theta is equal to secant squared theta, trigonometric identity. Then therefore this is secant squared theta. So in this case we can cancel out secant squared theta in numerator and denominator, and the a here and the first a, the denominator, so we could have the remaining would be 1 over a d theta, correct? So we have d theta and 1 over a. Now we have, since our 1 over a here is constant, we can take 1 over a outside of the integration. Then we have 1 over a, the integrand is in d theta, okay? The remaining would be theta inside the integration. So we have 1 over a, the integration of d theta is equal to theta, of course, plus c. So we have our theta here. Let's get our u back in our equation, in which from here our theta is equal to arctangent of u over a, correct? That's the inverse trigonometric function. So we have therefore 1 over a arctangent of u over a plus c. So this one now is the trigonometric, or the integration of du over a squared plus u squared. So if you have this kind of function, you can directly use this formula, or you can use trigonometric substitution. Now let's try to solve real number problem.